Have you ever looked at a beautifully curved object, like a jet engine or even a 3D model in a movie, and wondered, how do they even begin to measure its surface? Well, the answer is often found in this really powerful calculus technique. And today, we're going to break it all down.
You know, it's one thing to find the area of a flat square, but what about the surface of something like a vase or the fender of a car? These are the kinds of complex, curved shapes we see all around us. It seems like a super hard problem, but calculus gives us this incredibly elegant way to tackle it head-on. So here's our game plan. We're going to start with a really simple idea, just spinning a wire. Then we'll turn that idea into a rock-solid mathematical formula. We'll test it out on a shape we all know, a sphere. And then we'll level up to a much trickier problem. And finally, we'll zoom out and talk about what this all really means.
All right, so what is the core concept here? It's actually super visual and kind of fun. Just imagine you have a single piece of curved wire, right? And this curve is defined by parametric equations. Now what happens if you spin that wire around an axis? Well, it carves out a three-dimensional surface, and our whole goal is to figure out the area of that surface.
Now, this is where calculus really shines. Instead of trying to deal with the whole surface at once, which is way too hard, we're going to zoom in on just one teeny tiny piece of that wire, an infinitesimally small piece. When we rotate just that little segment, it creates a very thin band, almost like a tiny ribbon. The whole strategy is to find the area of one of these ribbons and then use an integral to add up the areas of all the millions of ribbons that make up the whole surface.
Okay, so that's the visual idea. Now let's translate it into the language of math, into our blueprint. And what you're about to see is that this big formula is actually built from two simple parts you probably already recognize. The first piece of our formula is the circumference. Think about it. As any single point on our wire spins around the x-axis, what shape does it trace? A circle. And the radius of that circle is just its height, its y-coordinate. So the distance it travels is just the circumference of that circle, 2 pi y. This gives us the width, so to speak, of our little ribbon. The second piece of the puzzle is the length of our ribbon. And that's nothing more than the arc length of that tiny little segment of the curve we're spinning. We call it ds. Now, I know that formula looks a little intimidating, but don't let it fool you. It's really just the Pythagorean theorem in disguise, finding the hypotenuse of a tiny little triangle made by dx and dy. So, let's put it together. The area of one tiny ribbon is just its circumference, 2 pi y, times its tiny little length, ds. Simple as that. And to get the total surface area, we just fire up an integral to add up the areas of all those infinite ribbons along the whole curve. And that gives us our final powerful formula. The surface area, S, is the integral of 2 pi y, our circumference, multiplied by that whole square root thing, which is our arc length element, ds. Now that we have this amazing tool, let's take it for a spin. To make sure our formula is legit, we're going to use it to find something we already know from geometry class, the surface area of a sphere. If we get the right answer, we'll know we can trust this method for crazier shapes. So how do you make a sphere? You just take a semicircle with a radius r and rotate it around the x-axis. We can define that semicircle with our classic parametric equations, x equals r cosine t and y equals r sine t. And to get the top half, we let t go from 0 to pi. The first step, as it almost always is to just mechanically find the derivatives of x and y with respect to t. Now we plug those derivatives into our arc length formula. And this is where the magic happens. Thanks to our old friend, the trig identity sine squared plus cosine squared equals 1, that whole messy thing under the square root just simplifies. It turns into just r dt. It's so clean. Now we can build our integral. It's the integral of 2 pi times y, which is r sine t, multiplied by our super simple ds, which is just r dt. We can pull all the constants, that's 2 pi r squared, right out in front of the integral. Then we just have to integrate sine of t, which is negative cosine of t. And now all that's left is to evaluate this at our bounds of pi and 0. And there it is. We get 4 pi r squared, the exact classic formula for the surface area of a sphere. This is so cool. Not only does it prove our parametric method works perfectly, but it really shows you the power of this calculus mindset. We just arrived a fundamental truth of geometry by breaking a big shape into tiny little pieces. Okay, so the warm-up's over. We've proven our method works. Now let's unleash it on a much more interesting curve, the asteroid. This example is really going to showcase the true power of our formula when things aren't quite so simple.
All right, here are the parametric equations for the asteroid. We're just going to rotate the part that's in the first quadrant, so theta will go from 0 to pi over 2. And you know the drill by now. The process always kicks off by taking the derivatives. This time, it takes a careful use of the chain rule. Now, when we square these derivatives and add them together, the expression you get looks like an absolute nightmare. It's huge. But here's the key. You have to look for the pattern. If you factor out the common term, you're left with that beautiful identity again. Cosine squared plus sine squared equals 1. And just like that, the mess disappears. After that amazing simplification, our arc length element, ds, becomes this much friendlier expression. We plug that and our formula for y into our main surface area formula. This gives us an integral with sine to the 4th power times cosine. And if you've been practicing your integration techniques, you know that is a textbook setup for a u substitution where u is going to be sine theta. After we do the u sub and evaluate the definite integral, we arrive at our final answer. The surface area is 6 pi a squared divided by 5. How elegant is that? We took this really complex, kind of weird shape, and by following our system, we found a precise, clean answer for its surface area. So, after all that, what's the big picture here? What should you really take away from all this? Well, it's about a lot more than just this one formula. It's about a whole way of thinking, a problem-solving strategy that is at the heart of calculus. The calculus mindset is all about deconstruction. It's about looking at a problem that seems completely impossible, like finding the surface area of an asteroid, and having the confidence to break it down into an infinite number of tiny, simple pieces. In our case, each piece was just a simple ribbon, and its area was just circumference times length. Integration is the incredible tool that just puts all those simple pieces back together for us. And this method isn't just for abstract math problems. Think about the real world. The bell of a trumpet, a massive cooling tower at a power plant, or even a piece of hand-thrown pottery. With the blueprint we've built today, you now have the strategy to start analyzing the surface of almost any shape you can describe. So the real question is, what complex surface will you measure next?